Alrighty, so now we'll move into explicit type conversions. And I think the last example of the implicit type conversions might have provided a little more motivation for this than what I intended originally, but we'll kind of see what's going on. So, explicit type conversion. Most languages, including C++, will provide some capability to do explicit type conversions. We might like to convert a value of one type and do a value of another type. And it's always, nice to explicitly state when we're doing such conversions and not kind of hide it and allow the compiler to just do it for us. The rationale for this is, if we're intending, if we're kind of taking for granted the compiler to make that conversion for us, just explicitly state it so that other readers know that the actual underlying conversion that's taking place was indeed intended. So we'll be able to do both widening and narrowing conversions explicitly, and such explicit conversions are also known as casts. So you probably heard that word quite frequently in your prior programming class, or maybe not. So to specify that a cast is going to be performed by the compiler, we're going to use C++ cast to do this. So you might have seen something like the C style cast. We're avoiding those. In this class, we're expecting you to follow this approach here. So we'd go ahead and write static cast, and then in angled brackets, we'd specify the type that we'd like to cast the value to, followed by the value to cast in parentheses. For example, if we wanted to convert the integer value of 5 to a double, we'd write static cast double and then provide the value in parentheses 5. If we wanted to find what the ASCII value of, say, the character of A was, we could simply convert that character to its integer equivalent, for which it's a symbolic constant for. Static cast int, provide the character A. And then we'd see, I think it's a value of 97 or somewhere around there. So when is this useful? Well, early on, this is probably going to be particularly useful in one of two ways. One, it's going to be extremely useful when we're performing when we're computing the different expressions where we would like to explicitly communicate to other readers that a cast or that a conversion is taking place. We should always use it then. Perhaps more frequently, at least early on in the class, when we'd like to perform floating point arithmetic instead of integer arithmetic. This is one area where we'll frequently need to employ a cast, at least early on in the semester. So let's just consider two integer variables, A and B, initialized to 9 and 5 respectively. If we were to write out the expression A divided by B, this would evaluate to 1 rather than 1.8, which is probably the value that we were indeed helping for. The reason for this is that integer division is taking place. What we really want to occur is floating point division, at least in this example here in application. I mean, there could be completely valid reasons why you'd want integer division to take place here, but that's not the case for the motivating example we're showing. To get the code, what we're considering mathematically correct in this instance, either A or B must be cast from an integer value to a double. And what this is going to mean is that we're going to have a mixed mode expression. So if I write static cast double A and then go ahead and divide the result of that expression by B, what's essentially happening is we're getting 9.0, because that is what the static cast will change A into, divided by 5. This is mixed mode arithmetic. So the wider type in this case is a double, so B is going to be coerced or implicitly converted into a double. So we'll have 9.0 divided by 5.0. And then the result of this expression is going to be what we were, in this case, intending, 1.8.